Welcome to today's paper reading. Today's paper is titled, Hallucination of Multimodal Large Language Models, a Survey. This paper, published on the preprint, is authored by Zechen and colleagues from Shou Lab, National University of Singapore, and AWS Shanghai AI Lab. The survey focuses on the phenomenon of hallucination in multimodal large language models, specifically large vision language models, LVLMs. These models, despite their significant advancements, often produce outputs that do not align with visual content, a problem known as hallucination. This issue poses challenges for practical deployment and raises concerns about reliability in real-world applications. Recent efforts have been made to detect and mitigate these inaccuracies, including the development of detection methods, evaluation benchmarks, and mitigation strategies. The survey also identifies current challenges and formulates open questions that suggest potential directions for future research. By providing a detailed overview of these aspects, the survey aims to enhance understanding and inspire further advancements in the field. The introduction of large language models, LLMs, has significantly advanced natural language processing, NLP, tasks, achieving remarkable progress in language understanding, generation, and reasoning. Multimodal large language models, MLLMs, also known as large vision language models, LVLMs, are now gaining attention due to their promising performance in tasks like image captioning and visual question answering. However, these models face a critical issue of generating hallucinations, which are seemingly plausible but factually incorrect outputs. The problem of hallucination in MLLMs is categorized into factuality and faithfulness hallucinations, with a specific focus on cross-modal inconsistency. Additionally, object hallucination in MLLMs is divided into categories, attributes, and relations, highlighting the need for a comprehensive survey to address these challenges and drive future research. In the context of multimodal large language models, MLLMs, hallucination refers to the phenomenon where the generated text response does not align with the corresponding visual content. This can manifest in several ways. First, there is category hallucination, where the model identifies non-existent object categories or incorrect categories in the given image. For instance, describing some benches and a fence that are not present in the image. Second, attribute hallucination occurs when the object categories identified are accurate, but the descriptions of these objects' attributes are wrong. An example is describing pink blossoms when the color is inaccurate. Lastly, relation hallucination involves all objects and their attributes being described correctly, but the relationships among them are incorrect. For example, stating that people are standing around her, watching when the actual image content does not support this relationship. Figure 1 illustrates the main content flow and categorization of this survey on hallucinations in multimodal large language models, MLLMs. The figure outlines the primary causes of hallucinations, which are categorized into four main areas: data-related, model-related, training-related, and inference-related. Additionally, it highlights the metrics and benchmarks used to evaluate hallucinations in MLLMs. Finally, the figure presents various strategies for mitigating hallucinations, including data-related, model-related, training-related, and inference-related approaches. Figure 2 illustrates the popular architecture of multimodal large language models, MLLMs. These models integrate both visual and textual data, enhancing the capabilities of large language models, LLMs, to perceive and comprehend multimodal information. The architecture typically involves two main approaches: the use of a learnable interface between pre-trained unimodal models, and end-to-end training from scratch. The training process for MLLMs generally includes two stages: pre-training and instruction tuning, which together enable the model to perform remarkably across various multimodal tasks. Figure 3 illustrates three types of typical hallucination in multimodal large language models, MLLMs. The first type, category hallucination, involves identifying non-existent or incorrect object categories in the image. For instance, describing some benches and a fence or some clouds that are not present in the image. The second type, attribute hallucination, involves accurately identifying object categories but incorrectly describing their attributes such as color or shape. An example is describing pink blossoms when the actual color is different. The third type, relation hallucination, involves correctly describing objects and their attributes but inaccurately depicting their relationships or interactions. For example, stating that people are standing around her, watching when the actual relationship in the image is different. The root causes of hallucinations in multimodal large language models, MLLMs, can be primarily categorized into four aspects: data, model, training, and inference. In terms of data, issues arise from insufficient quantity, poor quality including noise and lack of diversity, and statistical biases that lead to memorization effects. Model-related causes include a weak vision model that misclassifies visual concepts, a language model that prioritizes text over visual content, and a weak alignment interface that fails to properly bridge the two modalities. During training, the use of next token prediction loss may not be suitable for learning visual content, and the absence of reinforcement learning from human feedback, RLHF, can contribute to hallucinations. Inference issues arise from autoregressive generation where attention to visual content diminishes as sequence length increases, leading to responses that are irrelevant to the visual input. The chair metric is designed to evaluate object hallucination in image captioning tasks. It has two variants, chair, which evaluates per instance, and chair, which evaluates per sentence. This metric is still widely used in the era of multimodal large language models, MLLMs. The POPE benchmark converts hallucination evaluation into a binary classification task by prompting MLLMs with yes or no questions about objects in images. This approach offers increased stability and flexibility compared to chair. The POPE benchmark includes 500 images from the MSCOCO dataset. The MME benchmark is a comprehensive evaluation tool for MLLMs, covering 14 subtasks, including several related to object hallucination. Table 1 provides a comprehensive summary of the most relevant benchmarks and metrics used to evaluate object hallucination in multimodal large language models, MLLMs. The benchmarks are listed in chronological order based on their appearance on Arxiv. The metrics column specifies the evaluation criteria, with ACC/P/R/F1 denoting accuracy, precision, recall, and F1 score respectively. The primary focus of these benchmarks is to assess the extent of object hallucination in MLLM-generated content. Table 2 provides a comparison of mainstream multimodal large language models, MLLMs, on generative benchmarks. The table includes metrics such as chair, on amber, which indicates the rate of hallucinated objects, amber score which measures the overall performance, and Hallucian bench all ACC which represents the accuracy on the Hallucian bench. These metrics help in understanding the performance of various MLLMs in terms of their ability to generate accurate and non-hallucinated content. In this section, we delve into the various methods employed to mitigate hallucinations in multimodal large language models, MLMs. We categorize these methods into four main groups: data-based, model enhancements, training strategies, and inference techniques. Data-based methods focus on introducing negative data, counterfactual data, and reducing noise in existing datasets. Model enhancements include scaling up resolution, using versatile vision encoders, and incorporating dedicated modules. Training strategies involve auxiliary supervision, reinforcement learning, and unlearning techniques to refine the model's behavior. Each of these approaches aims to improve the accuracy and reliability of MLMs, thereby reducing the occurrence of hallucinations. Table 3 presents a comparison of mainstream multimodal large language models, MLMs, on various discriminative benchmarks. The table includes scores for metrics such as MME existence, POPE random F1 score, and Amber DIS F1 score, sourced from the original papers of these benchmarks. Key scores range from 120.00 to 195.00 for MME existence, 66.79 to 78.86 for POPE random F1 score, and 31.2 to 89.6 for Amber DIS F1 score, highlighting the performance variability across different models and benchmarks. The research on hallucination in multimodal large language models, MLLMs, faces several challenges. Firstly, Data-centric challenges include ensuring high-quality, diverse, and unbiased training data. Techniques for data collection, augmentation, and calibration are essential. Secondly, cross-modal alignment is crucial for maintaining consistency and contextual relevance. This involves developing advanced architectures and evaluation methods. Lastly, advancements in model architecture are needed to capture complex linguistic structures and generate coherent outputs. This includes enhancing visual perception and seamless cross-modal interactions. The study highlights the impressive performance of multimodal large language models, MLLMs, across various tasks. However, the issue of hallucination poses significant challenges, raising concerns about safety, reliability, and trustworthiness. This survey thoroughly examines the causes, evaluation metrics, benchmarks, and mitigation methods of hallucinations in MLMs. Despite progress, hallucination remains a complex issue requiring continuous research. The survey outlines promising future directions, aiming to provide a foundational resource for addressing hallucination in MLMs. It is envisioned that this survey will empower researchers and practitioners to advance research and develop robust solutions in this critical area. Thank you for watching.